Let's get started. So first of all, let's see. Make sure that you bring your homework to the front before the end of the class. Also, a few announcements. Because I'm still doing a couple of more midterm corrections, and that's going to happen early next week. So once those are done, I'll be able to post the solutions on Moodle, so you can check. That's one thing, and then also I sent out a survey yesterday. It would be nice if you can fill it out. It's anonymous again, so it'd be nice, and then be specific about the suggestions that you have. I was reading because there's some feedback already. I think I got some good suggestions over there, so that will be something I will be working on and then communicate with you all as well. Okay, and so today we're gonna do the Gibbs sampler. Actually, I think on Monday we're gonna carry on because this is taking a little bit longer than I planned. But today we're gonna talk about the MC diagnostics. Okay, so that's the slides material, and then on Monday we will talk about the paper that I asked you to read. So I think, yeah, so you have longer time to read the paper, try to answer the questions listed on the reading guide. So that will be more time, so you will have more chance to read them. And I posted homework 5, which is on Gibbs sampler. I made it due 2 weeks from today. It's only 2 questions, but the second one is very challenging, so I make it longer due date as 2 weeks. And next Wednesday, part of the lecture will be a lab to help you with that. Okay, so make sure to attempt as soon as you can. The part, I think the challenging part is understanding the model itself. So read read homework 5, the cover sheet, and then I will send an email about this. It's, the second part can be very challenging, and we're gonna have some lab time to help you with that. And then that actually leads to the next topic that we will be talking is the latent class model. So I think that's a good exercise as part of the homework, and then as a segue to the next topic. Okay. So all right, and also later today I will send an email about this paper, the project paragraph description that is due by Monday. It will just send one paragraph, depends on which type of the project that you're doing. So I talked about it a little bit on Monday, and I won't talk about it again, but in the email I would describe like 3 different choices. In each choice, if you have chosen one, what is expected in that description. Okay, so that's I will hope to receive them by Monday, so I'll be able to make comments and then see if there's any help that I can offer. And I noticed because of the surveys, because of the self-intro posts on Moodle, I think a big number of students in this class would like to do something related to Bayesian time series methodology. So by Friday, November the 3rd, because I'm working with independent study student trying to come up with about 15 to 20 pages of study material based on like her reading of a textbook. So we'll be able to produce some kind of learning material for those of you who want to do project related to Bayesian time series. So that's, yeah, because we're still working on it. So I think in 3 weeks time, we'll be able to post that. So just keep in mind that that might be something useful, but it's just gonna take a while before it can appear. And if you have any other, for those of you who are doing other topics, if you want to do some more reading, you can email me and then maybe start searching online yourself first, so you know like what roughly is available out there. And then I can also help point you to certain reading lists that you might find useful. Okay? So after today's class, until Monday, you should try to read the paper, explaining the Gibbs sampler paper, and then answer those questions, and then start thinking about your project, and then try to come up with either the research question, if you're doing analysis, the research question, the data set that you're doing, and then also like the Bayesian methods that you're gonna use, okay? Things like that. So I was in an email about all of this, and then, all right, so for today, we will be doing oh, before we start, sorry about that. Let's talk about the normal idea first, the Pygmalion study that I asked that you to to at least read through yourself and then talk to the groups that you get assigned to. So this is back in the normal, okay? It's the two parameter normal case where you have two groups, one control group, one experiment group, and look at whether the teacher's expectation going to impact the students or children's academic development. Okay, so just going to bring it up for you. So this was the data, and this was the summary statistics. And the problem back then, if you want to do frequentist analysis, you only have very small sample size, as well as even if you have large sample size, you might need to make other assumptions, saying like the means are the same in order to make some valuable inference. So it would be natural to start doing a Bayesian way. So this is what we had back then. So the idea is I asked you to read through the, sorry, it's taking some time. So for today's class will be, for the beginning will be talk about how you were doing the analysis, or how actually in the slides, in the example, what they're doing. So anyone? I hope you got the chance to read. I did read a comment from the feedback that this kind of project might be useless because no one is doing it, which I'm not asking if it's true, but I will figure out, and I would like to receive some feedback in terms of how I can make that. I mean, I know everybody's busy and then you have other stuff going on, but the course itself, I mean, it's challenging for most of the people, I think, and then if you don't do stuff before the lecture, you're just gonna get more confused after the lecture. So I would like to ask if you will be able to spend some time, at least do the stuff that I asked for. I think that will smooth everything for yourself as well. Okay. Anyway, so even if you haven't talked to any of the teammates, but I hope you make the effort to read it. So what do you think of this particular approach over here? So earlier I presented the data. Here is a list of questions that people might be interested in asking. And I posed the question, and then after that, I showed in the analysis, particularly in this Bayesian approach, what is this question related in terms of probability? Okay? So for example, is the average improvement for the accelerated group larger than that for the no growth group? Then we're asking the question that whether the mean, because each of the, like the 6 observations in each of the group, they are the change in score, right? So the question is the same as asking the posterior probability of the accelerated group, the mean of it, mu A, larger than the mean of N, okay? So, and then of course you can have some other questions. Maybe I'll bring next slide. So this is what we had. Any comments on this, or like based on what you have read? What do you think the approach? Or you can just restate what is done and then give some comments in terms of, do you think this is a reasonable approach? And do you think the computation is a burden? Et cetera, et cetera. Yeah.
Well, I thought the made sense where they were assigning the kappa and then be like 1 and yeah, that.
Right. Okay. So here, so Katie's talking about the second bullet point over here. If you don't have a lot of faith in the prior that you put on, so first of all, the prior that in this example they put on is they believe the mean is at 0. Okay, they think like on average the change is 0. So they start with that, but Katie's point is that now they're actually trying not to put a lot of faith, which is non-informative. So they're playing with this kappa. So what is kappa here? It's the prior sample size that we talked about in the normal model, right? So here you have kappa 0, you have 2 kappa zeros, A and N, because you have 2 groups. So in this example, they because they don't want to put a lot of faith, or they don't have a lot of faith, so they don't want to enforce that belief. So they actually only set prior sample size to be 1 in both cases. Okay. So back then, I think we were discussing, I think it's Nick's question back then about, and Eli's as well, like what the kappa 0 is really doing. So we're talking about, this is a prior sample size that you can put on, even though you're not generating like new numbers from the prior, but this kappa 0 is trying to control how like say how much belief you have in the prior. So if you think of it in terms of a prior sample size, you're doing, say, we think the prior covers, say in this case 1, covers 1 sample like amount of information that you believe that is going to be there for the prior. Okay, so if you put 1 everywhere for both cases, you're saying that I don't believe that much, but I still going to use the prior. So I want to ask you, so what's the sample size here? Both of the cases 6, right? So 6, so what that means? So you have just done the derivation, so I hope you remember about this n. So n and kappa 0, and then kappa n, right? So this is prior, like the sample size, prior size, and then the posterior size, right? So here, kappa 0a equals to kappa 0n equals to 1, and we also know that na equals to mb is only 6, right? Yeah, so the sample size, both of them are pretty small already. And then that's why, say, if even, say, for example, you know from somewhere else that you should believe that the means are 0, and I have a really strong belief in that, you might want to take kappa 0a and kappa 0n to be, I don't know, 10 or even larger. But a lot of times you should think about how large the sample size, right? I mean, you shouldn't override too much. So because the sample size are only 6 for both cases, if you put 6 for the prior size, it's probably very large enough because it's going to drive the inference for that. Mm-hmm.
Should you ever make prior sample size larger?
Right, so I would say, so here this is non-informative because they don't have extra information about it, but I think there are cases that if you know from other studies that you have strong information, strong belief in that, you can always make it. But so this will be, I mean, for those of you who will be more interested in doing actual analysis, you might just go back to try different kappas over there, and you can see the changes in the analysis in the end, right? So those, I mean, again, in class, we try to cover like some of the methods, some of the theories, some of the derivation, but then for examples, we only probably can present one version of this, say like I'm doing kappa 0 equals to 1 everywhere. But for those of you who are interested in, say, for Serenity, why don't you try larger ones? Those will be open-ended questions that you can go back to check. And then I think those will be related to your project as well. If you're gonna do a very applied work, the key question, one of the key questions there will be how I'm gonna set up my prior. In class, we talked about the most basic ones, right? But then the actual analysis itself entails so many other factors. And I think you need to be motivated yourself to try to explore more and always ask questions, okay? So what about the third bullet point over here? What is the standard deviation? Mm-hmm. Yeah, I think, what do you think? Can we have 0 over there? Mm-hmm. Yeah, so I think kappa 0 can be 0. Like that's just representing. The thing is, I think mathematically. So what is it? Okay, good question. So what does it do if you gonna have? Let me bring this back really quick. Right. So this is what I asked you to do for the homework, and you submitted today. So kappa 0 being 0, what does it mean? Mm-hmm. Kappa n will just be the sample size, right? So things change, I guess, mostly for, I mean, pretty much everywhere. Like kappa n is changed, mu n is only be, mu n gonna be y bar, you're just using the data to make your inference, okay? But like based on the example earlier, that version of analysis, you take n to be, you have n to be 6 and kappa 0 to be 1. So that little change actually changed a lot. That's what I was trying to say, that because the sample size is so small, kappa 0 to be 1 is actually not small at all in some sense, even though it's still non-informative. But just think about, say, this is like a made up example, but if you think about this to be 6, right? And this to be 1, and then mean, I don't know, say if it's 5, and then if mu 0 is drastically different from the mean of the data, and then you put 1 sample on that, 6 sample on that, say over here, it's, I don't know, 100, then it's gonna affect a lot, mu analysis, mathematically, right? And then of course, if you do the simulation, you will see that the inference is gonna be, even though, so this will be the case that even though you still have a very small prior sample size, but mu 0 gonna affect mu n a lot, and then that might, I don't know, might be a good choice, might not be, it depends. Okay? So those will be the question that worth answering. Yeah.
One of the questions that I'm still trying to wrestle with is, in our examples so far, we've always used integers to represent things like kappa naught, like the prior sample size. Mathematically, I don't see any reason why that has to be the case, but I feel like the interpretation of a prior sample size would be really hard to do. Is it a convention for when you use integers in those cases?
Good question. Actually, I don't think I know the answer, to be honest, because a lot of times you will see that a lot of times you, like if it's non-informative, you just put 1 over there to show that it's very, like you don't have a faith there. But I think mathematically or even intuitively, I think it makes sense that if you want to choose a non-integer value, that will still be fine. Because again, so n, the sample size, the data sample size is always integer because that's what you get, right? And kappa 0, you really want to just use it to represent your prior, your faith, the faith in your prior. So you can, I mean, integer makes sense because if you think of it in terms of size, that makes sense. A 1.5, say. So that's another question. Like if you choose kappa 0 to be 1, which is what's done for you in the slides, but if you just change it to be 1.5, I would guess the results probably are very similar.
I was thinking an example of maybe you have some data that shows a very different, like a very high mean or something like that, and you want to weight it even less than 1.
Oh yeah, right. Good point. Right. So look at this, like this particular form that we have seen, and you have been doing the derivation. You realize that when you put a prior, it's so many. So there are 2 priors here. First of all, one for normal, one for gamma, right? So right now we're talking about kappa 0 and mu 0. That's all about the mean for now, right? And you see that in this, the effect of it is a product of it, right? So I guess Eli's question is, oh, if I try to say mean is 100, which is very unlikely because the change of the test. But anyway, I'm just like making an example over here. And then if you have some like dramatic case that you're gonna have a really large or very small mu null, then the kappa null, like you said, if you want to do 0.1 instead of 1, because I don't want to have that, that's totally reasonable, right? But again, I think it's combination of things and then it requires trial and error. So it's not like a one-time analysis. I understand like right now, just because the way that it's being presented and then the time pressure of everything, I think you only see one version of them, but I would suggest you to think of the homework questions, especially the applications, as just one way to do it. And then the question is structured in the way that they ask you step by step, so you don't get sidetracked, so you know what to do. But you might have different ideas as you go along about it. And then that will be definitely useful and interesting to think what you would have done differently. And then I think that's part of the course as well, as much as you can do. Okay. Cool. So let's see. And then you still have the other part, right? You still have, so all of the second part over here is about the posterior for the phi, which is combined from the data and the prior for the phi, right? So this is V null. Remember, is the prior sample size for phi, and then n is the sample size. And then that again is a combined inference from the data and the prior over there. So let's keep on looking at the example a little bit more. I mean, it's not a very complicated example, but does talk about ways to put in priors here and there. So what else? Any other comments? So here, just show you what they, so you notice that here you don't even need R to do it, because for the normal gamma, normal/gamma normal case, everything is conjugate. So as long as you have the data, and then also the prior information or the prior distributions that you put on, everything will be completely solved. But in the end, if you want to make draws, you're still going to use the multi-count approximation. Okay, so that's why so far I think up until this point, so down here, if you're trying to do the predictions, say, just try to do the posterior, then you're doing multi-count approximation over here. So this is for the accelerated group. The other one is for the no growth group, and then it is straightforward enough to do. But I do want to emphasize that, like analysis problem like this, it combines a lot of stuff that we have learned. You first of all need to know, even though you might not remember all of the terms when you're trying to do the final Bayesian analysis for the posterior, but if you're given the form and if you're given the data and then the prior that you come up with, you should be able to come up, say, with the posterior in this way. And then in the end, you should be able to sample it. And that's multi-count approximation that we have learned so far. Okay, so, right, so hopefully next time, if some analysis like this is assigned, I hope everybody will get the chance to really read them and then get the chance to talk about it in class. Okay. Okay, so the stuff that we're going to talk about today is the diagnostics. So last time in class, we did start talking about when you try to run a Gibbs sampler, you are doing it for a long time. You're doing it iteratively, first of all. And then you will need to do it a long time. And in order to verify if you have done it good enough, there are different checks that you can do to see if your Gibbs sampler is good enough, and that's what we call diagnostics, okay? So think of them as chains that you're doing. So last time we're doing the normal with mean and phi case. So we're saying that for a Gibbs sampler to work, you start with mu 0, phi 0, okay? And then you're gonna draw, say, your first mu, your new draw of mu, given, so remember this notation, we say everything else, that everything else includes the phi and the data, okay? That's a normal. And then you draw the second, so here is your phi, the 0 phi. And then you're gonna draw your first phi by mu 1 and y, which is gonna be a gamma, okay? So this will be the first draw that you do, and you do it for second draw iteratively until you have t, and then t is using capital T. Yeah, so t here, you can think of it as time, you can think of it as iteration, but in the end, you're getting a large number of samples of mu and phi in that way. Okay, so what we talked about last time is that once you have done this, you get good joint approximation and you get good marginal approximation. Okay, so what it means, so say now I'm doing a Bayesian analysis for some data, and I put independent priors, and then I can use a Gibbs sampler, independent priors for the mean and the variance or the precision. And now I run my analysis, I run my Gibbs sampler, and in the end, the questions that I want to answer may be, okay, what's the mean like, right? Or what's the precision like? Or what's the joint is like? So the Gibbs samplers guarantee you that once you have done it properly, which means that it needs to pass all the diagnostics, which is what we're gonna talk about today. But once those are done, you will be able to summarize based on the draws that you have from the deep sampler. Okay, so say here, if T is 10,000, okay, so the question now is, can we use the 10,000 draws? So we have 10,000 draws for meal. We also have 10,000 draws for feed, but can we use all of them to make inference? So this is what we want to talk about today. And the motivation, or like maybe one way we talked about it before a little bit, but just to echo it again, Markov chain, Monte Carlo. So deep sampler is one of this MCMC. It's one method of the MCMC. So the Markov chain, that comes into, like, why we have that is because you're sampling things iteratively, right? Like the previous draw depends on, or like the current draw depends on the previous draw, and then things are done iteratively. So that's the Markov chain part, okay? And the Monte Carlo part, like what we have learned before, and the biggest difference I was talking about, or biggest takeaway back then, is you need to have independent draws to make your inference, right? So you can think of this, you can think of MCMC as, now say Gibbs sampler as an example. This Gibbs sampler gives us, say, 10,000 draws of both parameters. We get them through an iterative way, right? We get mu and then get phi and then get mu and get phi. And then it's Markov chain because current depends on the previous. But in order to make the inference, especially through the Monte Carlo approximation, we need to get rid of the dependence that we introduced because of the iterative procedure. Okay? So that will be one big thing that people take care of. And I told you before that, well, instead of saving every draws, say this 10,000, I'm saving every 10 or every other 10, or every, say maybe every 10, every 50, et cetera, depends on how much dependencies are there. Okay? So this will be one diagnostics that we will do, but there are some others as well. So we'll just go through them one by one. But the big motivating picture over here is because we have got the Gibbs sampler doing by Markov chain and Monte Carlo together, but in the end, in order to make the inference, we need to take care of certain aspects of it to make sure that the inference will be valid. Okay? All right, so okay. Other question you might be asking, say, how long should we run the chain? And then how well do we think the chain is converging or not? Okay, so when we're talking about converging, we're talking about, say, we were trying to come up with a sampler that can give us a good approximation to the true posterior. Okay, we call it as the target or stationary distribution that we're trying to approach to. So the target distribution, first of all, should not depend on the starting point. And then other questions will be like, oh, I don't know, like 10,000 rounds are good enough. Should I do more? Should I do less? Because the more you do it, the more time it's going to take, right? So there's like this trade-off over there, how much you want to do. And even so, sometimes you want to say that, like the second bullet point over here is like, we want to know that the sample is going to converge to the true joint distribution in the end. So how can we tell that it's going to converge? So those will be the questions. And then I would say each of this is actually being answered by one measure that people have developed so far. So we're going to go through them. And this, you see, will become standard practice for you to evaluate whether your MCMC has done a reasonable job. Okay? All right. So first of all, I think I talked about this a little bit last time as well, is called the burn-in process. So I think Eli in the front last time was asking, can we try with different starting points, right? Like, yeah. So back then my answer was, if your distribution, if your draws, if your sampling, if your sample is actually approaching or like approximating the target distribution well enough, the starting point shouldn't matter. Like say if you start with 10, I think we saw it last time with the example, right? Like in the R code, the demonstration that we did. We start with some number and you see that very fast, the starting number doesn't matter because the chain actually goes to the district, like goes to the area pretty quickly. So, but still, sometimes it's probably going to take a while before the parameter going to be able to, like the draw is going to be go to the actual sample space that you want to explore. So a standard practice is to throw away some of the beginning draws that we don't want them to affect our analysis in the end. Okay, so standard practice is called burn-in, and the idea is you're going to throw away the first P% of the draws. The default is 50%, and then the rest will be kept for making the inference. Okay, so this particular initial step over here is trying to take care of the fact that we don't want the initial values to affect the analysis, because you might start the chain at any time or at any value. You might not start the chain at the right value that you want it to be. Plus, you actually don't know if the chain is good enough anyway. But still, the general idea is that based on the plot, you will see that sometimes the starting points actually matters a lot. So we don't want to include those at the beginning. Okay, yeah. So maybe just, yeah, I can try to draw something over here. So last time we're looking at, remember, like the draws were like this. That's a particular typical way that people try to use to evaluate the MCMC. So we call it trace plot. Okay, so I think last time someone was asking, oh, why don't we do like histogram or stuff? But this type of diagnostics is really trying to see if the chain is doing well enough. So we don't do histograms. We're trying to see if each parameter is doing, like the sampling is doing a good job. So if you look at this, I was trying to say that, suppose, this is just suppose this is the real region, the truth, where the parameter should be. Okay, suppose this is the truth. So you see that this is just an example that I start with this point, right? It takes not so much time, but it takes like some steps before I can get to that range and then finally stabilize. Okay, so this would maybe one example. But you might start a chain at a different point, say here, because you don't know any better, you're just going to start with it. And then if the model is good enough, the sampler is good enough, you should go down, hopefully quickly, and then converge over here as well. Okay? So this is a general idea that, you see, depends on where you start. You might have some percentage of the draws are not good enough in the front at the beginning. So that's what we do. And by default, like default value is 50%, but you really should look at the graph to decide how much you want to throw away. Okay? But like a good starting point will be, okay, I'm going to throw away 50%, and then I will keep the rest to do my analysis. Okay? So this is the general idea. So again, this is, I was drawing it, so you might not believe that is going to happen in practice, but trust me, some situations you might see that, and this is the biggest cause of why we want to do burn-in in the first place. Okay? All right, cool. So this is burn-in, and that's the initial step. So the particular example that I'm using for today is actually from the textbook. Is thinking about now, if you actually have a 3-component mixture model, meaning that I'm gonna have, say, here, we're not talking about the model itself. This is just what's given to you. This is the posterior. It's a mixture, 3 different normals combined together. So the notation here is, let's see. This is normal, mean at -3 and variance 1/3, okay? This is normal centered at 0 with the same variance. And this is another normal centered at 3 with the same variance, okay? So now I tell you, this is what this is the true posterior, okay? The true posterior is a combination of 3 different normals. And look at the weights here, different color, yeah. So 45% for the first and the last, and about 10% for the middle one, okay? So this notation is telling you, so this is a made up example in a way that I tell you this is the truth, and now I want to sample it. How can we do a good job using MCMC, or in particular, GIP sampler, okay? So don't worry about like how the data model was. It's just now given to you that it's going to be a mixture of 3 different models, 3 different normals. So something very useful to do, which is going to be the like the topic of next chapter, is think about it in terms of a latent variable. Okay, so think about how you're going to draw this. What do you think? If I tell you that this is the truth, I ask you to use Multicount Approximation, what are you going to do? So mu has 45% chance coming from the first normal, 10% chance from the second, and 45% chance from the third. What are you going to do? In not Gibbs sampling, in Monte Carlo. This is the first one, second one, and third one. What do you think you're going to do?
I'll take a random number between 0 and 1. It's between like 0 and 0.45.
Okay. Yeah. So Paul's, next time I will walk over. Sorry, I forgot. So Paul's point idea is, okay, I'm going to take a random number from 0 to 1. Okay. And then, so think about 0 to 1. 0, 1. And then because, think about the weights over here. It's 45%, 10%, and 45%. So, oh, I'm doing a really bad draw over here, but I was trying to say that, sorry. I was trying to say that this is 45%, this is the 10%, and this is the 45%, okay? So the idea is that if you take a random number between 0 and 1, it's from from a uniform, right? Yeah, I should have asked it. Yeah, from a uniform, a continuous uniform from 0 to 1, and I will see, okay, if the number that I draw falls into here, I'm gonna go from the third. Okay? If the random draw is from here, I'm gonna go from the first. Okay? If the random draw is in the middle, I'm gonna go to the second. Okay? So this is doing it in a 2-stage thing, right? I first decide which normal I'm gonna sample from, and then I'm gonna sample from the normal. Make sense? Yes? Yeah. All right, so this, let me just explain it again. So if you read this, let me just do it again. These are the weights, they add up to 1, okay? And now I ask you that how are you gonna sample this? And you know that this is the truth. So it's a 2-stage procedure. And the first stage is deciding from which component I'm gonna sample from, okay? So this is the first component, second component, and third component. And I know that I need to have 45 chance to come from the first component, 10% chance from the second, and 45% from the third. So I will first, so what Paul suggested is you're doing a uniform random draw from 0 to 1. And then if it's between 0 to 0.45, I'm gonna choose from the first one. If it's between 0.45 to 0.55, I'm gonna choose from the middle one. And then if it's the rest, I'm gonna choose the last one. So this way, if I'm doing a uniform over here, it guarantees that I'm having these weights in the right place. Okay? So what this is doing, you can think of this as a latent variable idea, that if you introduce a delta equals to 1, 2, 3, indicating which component you're choosing from, then you're pretty much doing a 2-step thing, right? The first step is over here, deciding which one you're doing. And then the second step is conditional, because now I know which class it should come from. Then if it's the first one, then I'm gonna from the first one. If it's the second component, it's gonna for here. If it's the third component, it's gonna be from here. Okay, yeah, so this is a very common technique, and I hope the first time, this is probably the first time for many of you to see this, but this again is very useful, and then for the sake of sampling, this is a widely used method. All right, so what this tells us is, if this is the truth, we can use Monte Carlo to sample it, right? And they're independent, because every time I'm doing it independently. So if I say I do this procedure for, say, S number of times, they should look very similar to the truth. Make sense? So in the past, the multicolor approximation that we have done, there's nothing complicated as this. You don't have mixture, you don't have different components, you know exactly where you're sampling from. Say back then, you might have sampled things like what is normal 5 and 100, then what you do will just be using the R norm and then taking so many samples with the mean and standard deviation, then you're good to go, right? That's what we have seen so far, yeah. This one is more complicated. It's a mixture, meaning that it can come from the first one with 45% probability, from the second one 10%, and from the third one 45%. And the way that you do it is to introduce a latent variable so that you're going to decide which component you sample from, and then you sample from that component. But no matter what, you're doing multi-color approximation, okay? Because everything is done independently, and you do it multiple times, and then you should be able to summarize what it looks like, okay? So any guess what it would look like? Roughly the shape of this mixture? It's 3 normals. You know the 3 normals. They're given to you. You know the probability from each of this. To total one. Sounds good. Yeah. So first of all, notice that they all have the same variance, right? So the spread of each of the little mountain will be the same. So roughly, so this is 0. This is -3. This is +3, right? So these are the 3 means that I will sample, or like I will center at. So roughly will be something like this, right? I mean, the density itself, I would imagine it would look like this. So what I described so far, all of this, with the help of Paul, will be, if you do MC multicolor approximation, if you do a histogram, like the histogram should have this particular shape. I mean, roughly, yeah. Not exactly, of course. There's some variation, but you should see something very similar. Okay, so if you do that, so this, the histogram itself are the draws, while the density over there is just using the density function over there. But it's pretty much matching what we were imagining what it would be. So if you look at the x-axis, that's just telling you the mean. The y-axis is the density over there. So it's about, because it's 45%, 10%, and then 45%. So you will see that, oh sorry, 45% over there. So you will see that that's how the height change is telling you. Right. So this is the truth that we know, that the multicolor approximation would work. And in particular, there is a trick here that you should introduce a latent variable over there to complete the steps. Okay. But now the problem is, of course, more than that. I want you to think about how can we do, let me just bring this back over here. How can we do a multicolor, Markov chain multicolor over here using Gibbs sampler? So I give you some information here first. So first of all, this is what you have seen before. Okay? These are the 3 different means given which component it comes from. This is the full conditional for mu, right? Okay, so this is what you're given. So now you introduce a new parameter, which is this indicator. And delta takes 1 or 2 or 3. So how can I come up with the full conditional for this delta? If I want to use a Gibbs sampler, I need to come up full, full conditional for each of the parameter, and then I round it, right? That's what we talked about last time. So now you have 2 parameters, the mu and the delta. Mu is straightforward. We know what it is. It's given to us, and these are the 3 over here. But what about the delta? Delta is the latent variable, can take 1, 2, 3. If you know the joint distribution of mu and delta, you will try to derive it, right? Like what we have done so far. If you know what mu and delta given y is, I will start trying to derive it, right? So this will be, say what you know, and then you try to get mu given, delta and y, and then you try to get delta given mu and y. So both of this are full conditionals. So in theory, what you're gonna do, you're gonna write out the joint and try to find all the terms related to delta, and then try to recognize what it is, right? Based on what we have learned so far. Is there a quicker way that you can do this? I mean, I kind of presented over here for you, but I still would like you to think, instead of trying to write it out one by one, is Bayes' theorem useful over here to come up with the posterior or like the full conditional for the particular delta here? So what's on the top here? The product. I write it in terms of d norm. Even though I write it in terms of d norm, but it's really talking about the likelihood, the contribution from the likelihood for this delta, right? So likelihood, this is somewhat like the prior. And then down here, because I only have 3 different d, then I'll be able to sum them up as a way to use Bayes' theorem. Okay, so let me pause here a little bit. I think this might be hard to understand for the first time. So delta can only take 3 different values, 1, 2, 3. That's the 3 different components, right? So the full conditional is trying to tell you what's the probability that I'm gonna go for the first, or go for the second, or go for the third, based on the data and the prior, right? That's what I'm trying to do with the full conditional, similar to posterior, yeah. So if you think in terms of that, I have 1, 2, 3 to choose from. Which one I'm gonna choose from? I'm going to use Bayes' theorem. Bayes' theorem is going to tell me what's the probability of choosing from the first one, what's the probability of choosing from the second one, what's the probability of choosing from the third one, and you have them separate. The sum of them will just be the normalizing constant over there, and then you're going to decide what you're going to choose. So to rewrite it, you can think of this as delta equals to 1, given mu and y. It's going to be delta equals to 1, given y, and then the normal, so I would say the likelihood, given that delta is 1, over delta is 1 y times likelihood delta equals to 1, plus it's possible that delta is 2, plus it's possible that delta equals to 3. Does this make sense? Mm-hmm. Yeah. So in the full conditional, given everything else, I'm trying to evaluate how likely I should decide that it comes from the first component, right? So by Bayes' theorem, on the top, it's the prior times the likelihood in some way. In the bottom is the sum of all of those when you take values of delta to be 1 or 2 or 3. Okay? So this is a like simplified format to write it, but you can also list them like delta equals to 1, delta equals to 2, and delta equals to 3, one by one. Make sense? Yeah, I think, so again, I think earlier I did ask you to try to read this through, so I guess maybe I asked too much, but still, again, I feel you really need to do a little bit more preview, otherwise the lecture will be slowed down, and then things won't be able to explain well enough. But you still get the chance to do it, like do the review after this, but this is a general idea of what you can do if you have multiple components, and then you introduce a new parameter over here as the indicator, and how I can incorporate that into my Gibbs sampler. That's the way to do it. Okay, all right. Right. So this is my MCMC draw. Not really good, right? Yeah. So see that I run it for 1,000 draws. So this MCMC is from this. I derive from here, and then I run the MC, like the Gibbs sampler, like iteratively. I run it for 1,000 draws, and these are my starting points. Okay. Yeah. So not yet capturing what I wanted to do, right? So there are multiple things you can do. You might want to run it longer, or you might want to start it at a different point. Even though we usually talk about starting at a different point, wouldn't matter, but it really depends, and again, depends on how much we're throwing away at the beginning. Okay, so what we've been doing so far is this is the truth. We know what it is, and you can generate it. You can do Monte Carlo, and then you should recover it well enough. And now we come up with this Gibbs sampler scheme, introducing one extra parameter over here as the indicator, and then we do MCMC, and you see the results first time. Not really good. What else we can do? Another thing that I want to show you is this is the Monte Carlo samples, okay, of the mean. Okay, so what do you think of this? Do this match what we thought it would be? In what way or what not? Yes.
They're clustered around 3 points as we expected them to be. And it's denser, higher probability areas also like we expected.
Right. So the reading of this graph is you should look at the y-axis, which is telling you the mean, right? And we know that the mixture, what was the mixture? The mixture is 45% from normal -3 over 1 over 3 plus 10%, 0, 1 over 3, and then plus 45%, oops, sorry, and 3, 1 over 3, right? So because the Monte Carlo approximation was really good already, so on the plot of the Monte Carlo samples of the mean, we should expect that there's 2 big dense part around -3 and around +3, right? And then the middle part is around 10 and it's less dense. And if you were able to count, say how many points are over there, the percentage should be about 45%, 10%, and 45%. Make sense? Yeah. So think creatively what you can use to evaluate, and this is called trace plot. And there are other ways to do trace plot that is going to give you something like that. That will be fine as well. But this, again, is still for Monte Carlo, so everything looks good. And this is the MCMC plot, which is pretty bad. And it's not surprising because remember back here, this was bad already. So let's look at some other like measures. So trace plot, What do you think of this? What's funky here? Or in the ideal trace plot that is doing a good job, what it should look like. I guess it should look like this one, right? Unfortunately, it's not. So what's the problem here? And what do you see the trouble with this particular chain that we have done? It starts from -3, right? So by the way, I guess I forgot to say earlier, the x-axis is the iterations. Okay, so this is like MCMC, I run it for 1,000 times, right? So this is my first point. I start with -6, and it jumps to -3 pretty quickly. But unfortunately, it stays there for so long until, I guess, 700-ish. And then all of a sudden, something happens. It jumps to +3, which is actually good because we know that that should be another area to explore because that's the truth. And it stays there for like it's like 200 draws and then come back again, right? And nothing really in the middle either, right? Yeah. So this, I mean, again, this is kind of eyeballing at the beginning, but I want you to get used to the idea of thinking in terms of chain and how the chain is exploring the parameter space. Because we want it to be 45% around -3, 10% around, on -3, sorry, over here, 10% around 0, and 45% around 3, right? So in an ideal world, you're gonna have the chain go up and down, sometimes in the middle, go up and down, sometimes in the middle, right? But in terms of time, you'll want to have 45% on the top, 10% around the middle, and 45% down there. So a good chain would look like something like that, okay? And so the problem here, what do you think of this? Why I stay here for so long? Mm-hmm.
That's what doing anything to it, right? So that like we didn't burn anything.
Right, we haven't burning anything yet. Here is just 1,000 draws. The burning process, you should throw away, say the first 50%, something like that. So yes, and the problem, I guess, especially from this plot, is they're so sticky. This is another term we're gonna learn soon. Sticky in a way that the chain, like the adjacent draws, is so similar to each other. The dependence is so high that it's so hard for me to move away from it, even though that I know the truth shouldn't be here. Make sense? Mm-hmm. Yeah, so for some reason, it goes up around this point and then explore a little bit and then come down, yeah. I guess another drawback of this particular MCMC will be, we probably run it for too short, right? If you run it long enough, we might see a better picture over there, yeah.
So you take it off base with this kind of case, be a time that we want to use the method of like drawing K and then taking the K plus 1 value and then drawing where it's at and starting again.
Okay, very good point. So Eli's point is, so this is running one chain, right? And we're summarizing across this one chain. I guess Eli's point is, how about instead of sampling 10,000 draws in one chain, I'm gonna start 10,000 chain. Is that right? Something like that? Yeah, and then I'm gonna summarize from the last one, like the last draw from each of the chain. I should have independent draws. They should be able to explore the sample space well enough. That's a reasonable choice. Make sense? So the immediate drawback of that is too much computation, right? You're running it, and for each of the chain, you might have to run it long enough so it's converged somewhere, right? So this is actually what I want you to think hard about from the paper that I asked you to read by Monday. So that paper was, so the Gibbs sampler itself was developed back in 1990, okay? And then all of a sudden people start to write papers about it, try to do different analysis and exploration. So the paper that I asked you to read is called Explaining the Gibbs Sampler. It's published in a journal called The American Statistician. It's very approachable. Like there's some math and derivation over there, but a lot of applications and then simulations for you to read. So it's definitely accessible. And that paper, just 2 years after the Gibbs sampler, actually talks a lot about like things back then, what people were doing. So what Eli's suggesting is actually what people were doing back then. I should run so many chains, and I just pick the last one from each chain, and then I'm gonna have a sampling, like a good approximation over there. Yeah, but you will see that nowadays people don't do it anymore. There are many reasons. I think computation is one reason. Yeah, and then so just go back to read the paper, and then let me, yeah, like on Monday we're gonna discuss various aspects of it. And over there's some other practices that are still being used right now, but there are many others being abandoned. I mean, things are changing. I mean, the field is changing as well, but there's still some good stuff in that paper that I think will push you to think how people in the first place came up with this method, and then how things are changed. I guess it's almost 30 years now. Okay, cool. So this is good practice looking at chains. This is a trace plot, and so many things we can do. We should do burning. We should throw away something. We should also like take independent draws. We should save every other 10 draws, so 50 draws as much as we can. And maybe we should run it longer. There are so many different things you can do about this, but this one is not good yet. Okay. So let me just tell you some other terminology over here. Stationarity is talking about how, say, like this definition, stationarity is about like the samples itself, and the sample distribution itself. And then when we talk about stationarity, so we have 3 different regions for the mean to be there, right? Negative infinity to 1, like roughly if you put it, so let's see. You have 0, 3, -3, and 3. And now I ask you to think of it like I'm gonna cut it over here and cut it over here, okay? Like -1.5, +1.5. If I divide my partition pretty much, the parameter space in this way, I define this to be A1, define this to be A2, define this to be A3. Based on the truth that we know, A1, the probability of A1 and the probability of A3 should be equal, right? Because it's about like 45% here, 10% here, and 45% over here, right? Yeah. So if we like, so here, this cutoff point is just trying to take the middle. So roughly they should be the same, symmetric. And then, so both of this, A1 and A3 should be equal, and they should be larger than A2, based on the truth, okay? So when we are talking about stationary or convergence, we're talking about that if your chain, say, go, and then goes into this A2 region, the chain or like the sampler itself should be able to move out from it because you shouldn't stay there for so long. Okay, so this is like a general idea of stationarity, and then that's also talking about convergence as well. And we also talk about mixing. That means that once you reach to A1 or A3, a good mixing of the chain will be that I can still bounce back and forth because they should be equally likely, about 45%. Okay, so those are some other terminologies over here, but again, I think you should think of it as the most intuitive way that you think of a chain, what a good chain should be. And then all of those terminologies here that we're presenting is just talking about some like formal way to define whether like what a good chain should be like. Mm-hmm. It does move out. Yeah, it does move out. So in actually, like, because you have 3 different regions, you should move out and move in like easily, right? Yeah. And so that's but then in this particular example, A2 is less likely than A1 and A3. So you can think of it as less likely to go in and more likely to come out, comparing to A1 and A3. Yeah. Mm-hmm. But what if, say, like this is the example that you have 45% in the first, 45% in the last, and 10% in the middle. But if you have 33, 33, 33 in 3 different cases, then you should just be equally likely to move around. Okay? Mm-hmm. All right, cool. And one last thing is the stickiness that I was talking to you about. It's just like how sticky they are, meaning that how easy or like how chains or how parameter draws are being stuck in one component for a while but not moving out. So we don't want very sticky chains because it's going to be too much stuck in one area, but the parameter space is much wider, and then you should explore that as much as you can. All right, so you might be wondering, how am I supposed to decide how sticky it is? Right? I mean, you can look at it and it's not doing a good job, you probably can tell. But we do have some other particular measure that is being used to evaluate if it's too sticky. And if it is, you might want to save every 10 draws or every 50 draws in order to get independent samples. So what we call this is ACF, autocorrelation function. It's autocorrelation because it's the same parameter. Okay, this auto is over there in that sense, but it's the same parameter but different draws. So this is trying to, so this draw, like this plot right now, is the autocorrelation plot for the Monte-Carlo. So because the Monte-Carlo draws, they're independent, right? Because we draw them, like the first example, they're independent. So you see that the autocorrelation with itself is 1, and with everything else dies down pretty quickly because they're independent from each other. So this is what we would like to have, okay? But MC, because it's Multicount Approximation, is independent. So this, you can think of this as the benchmark that we're trying to reach. So this is good to go, but you might wonder, based on the previous plots that we have seen, the ACF plots with the MC is terrible. Terrible in the sense that even if you're looking at the draw, the current draw, with the 30 draws later, they're still very much dependent from each other. Okay, so this plot, if you try to do this, this is an indicator telling you that, oh, like saving every 30 draws is not good, far from good enough, right? Because T and T plus 30, so this is lag, okay? Think about the value of like the difference between T and T, the next T, like you're evaluating. So based on this ACF plots, at least from this one, I think you probably would like to, I don't know, save even like 50, probably not good enough either. And then that just tells you that you have to run the chain really long. You should throw away maybe at least the 50% in the at the beginning, and then run it long enough that you can still save good number of draws after so many things being tossed out. Okay, so the ACF in R, just ACF, and then you put in whatever the like the vector that you save, all of this, it's going to return it for you, and this will be the indicator as where like how you're going to decide what the procedure you're going to do when you save every few draws or every, I don't know, 10 or 100 draws. So I was saying this is the goal. That would be great because this Monte Carlo. You should be independent from each other. And then this is terrible example over here. And you notice that they give you 2 dashed line over here, symmetric around 0. I think it's automatically provided, like produced by the R function. So pretty much this is like a threshold that you can see that once it draws between this, like say this, it drops down in this, those will be good enough. Okay, so this is like tune in over there for a particular ACF over there. So every time you apply this ACF function, you're going to see a plot like this, as well as a threshold, like a range over here. So say a draw, say like at one particular case, at the 10th draw, I finally draw into this. And even though everything else was still above, but once I start from the 10th, it's between this range, then that tells you that you should save every other 10 draws. Yeah, because it's like after lag 10, the dependence is being taken care of. I don't have to worry about it. Okay, so here I just give you a list of useful diagnostics and functions. Trace plot is what we have seen before. It's very straightforward, just called trace plot. Oh, sorry, I guess I just lied. Autocorrelation is autocore.plot, sorry about it. It's autocore, but ACF probably going to returns you the number, sorry about it. But for the plot that I show you, you're gonna do the auto core. And here are some other ones that I presented here. I think I will focus, because we don't have much time left, but I focus a few other things by the end of today. So we have seen trace plot, we have seen autocorrelation. This is super important as well. Based on the name, what do you think it means? Effective sample size. What do you care? Like say, now I have a super sticky chain and I try to like do some, so like the autocorrelation and then saving every other draws, that kind of procedure is called thinning. Like you thin the chain, okay? So you do thinning, you do like burning, you do different things. And you still want to know, say, based on all of the draws I have, how useful it is, or how independent they are. So this effective sample size is trying to tell you that among the draws, say after thinning, after burning, I only have 1,000 draws left, okay? Say this is what you have. And then using the effective sample size function is trying to tell you that now you have 1,000 draws. You don't know how good they are. But the R function is written in the way that they're going to tell you, based on this 1,000 draws, how effective they are, meaning that how you can think of the size in terms of how you can think of the effective sample size as the effective sample size of independent Monte Carlo draws that you have based on this 1,000 draws. So let me say it again. You have 1,000 draws that you're left with, and then you want to know how effective they are. Effective meaning that how many copies of independent Monte Carlo draws this 1,000 draws actually represent. Okay? So because ultimately we want to have large numbers of independent Monte Carlo draws so we can make good inference. Okay? But I was saying that even though you have done trace plot, you have done some burning, based on the autocorrelation plot, you have done some thinning, but you still don't know how good the remaining draws are, because you just have done like what you have, like you try your best to do based on the other diagnostics. So the effective sample size is trying to tell you, say among the 1,000 draws that are left with, if say the like the effective sample size is only 3.5, that's really bad, meaning that even though I have 1,000 draws available, I save them, I'm trying to use them to make inference, they really only represent 2.5 independent Monte Carlo draws that you can get. So either they're still very sticky, or it doesn't explore the space well enough. Okay, so this is, again, the end of story is that you want that to be as big as possible. Yeah, as big as possible. But sometimes, unfortunately, even though you run it long enough, and you do the thinning, you do the burning, it might not be good enough. And then effective sample size will be a way that you can evaluate how good it is. So in terms of code, it's pretty straightforward, just effective sample size. And then for this particular example, the example that we had, the 1,000 draws of this mixture of normal, unfortunately only worth 3. And that's why you see it's so bad. Okay? Because even though I have 1,000 draws, it's really only equal to taking 3 independent samples. Okay? Yeah, so it's very sticky, and you can see from the plot. So you see that like all of this, the diagnostics, they all together, they work together. If you see bad in one, like if you find it not good in one measure, pretty much everything else is gonna be bad as well. But so the story is you need to check all of them to prove that it is good enough, but you only need to check one to show that it's not good. Make sense? So you have 5 different measures that you can use. And then you need to check all of them to say that my chain is good enough. Check all of them, meaning that each of them is good. But then if you find one is not good enough, you should you should think about something else. Run it longer, etc., etc. Okay? All right, cool. So this is, right, there are a few other stuff I think I will pick up on Monday, but go back to read the slides carefully. And then the textbook has a section on this. They probably don't have a lot of material, so I'm trying to supplement the slides. And the R code for this particular slide is on Moodle. So you can try, and it's exactly using the same example, like the mixture of the normal. So you can try that over there, and hopefully that can help you figure out some of the technical parts over here. Okay, all right. Have a good weekend.